any doubt like how we are using which features need to be present in the CAM software and all? Anything you have any doubt, you can just ask me over here. All right, then okay, I'll just briefly maybe recap this thing, how to use the CAM software. Maybe quick revision how we are working. So yeah, so maybe I will just show very quickly. Maybe okay, yeah. So first thing is like we will the import the model and yeah, the first will the import the model or create the one, or maybe I'll just create one more time. The first thing we need to do is like we have to create the work plane. That is at the 0. That is nothing but the global origin. So it's created over there. So now we have to import the model or either import or create the model. So let's create the model over here. So we'll select this cone and then we'll import it or create in such a way that it's oriented towards the top. Uh, like the z-axis it's in such a way that from the z-axis, if the tool comes, it should be easily accessible for a tool, and there should not be any collision or overhead, something like that. Then maybe I will just modify the dimension a little bit. Uh, uh, 50. This might be 75. Uh, just give me a second. Yeah, so we set the dimensions, set height and all. So we import the model and now we orient it such a way that the Z from the Z-axis, the tool will come and it's reachable for all, from the Z-axis direction. Once it is done, the next thing is like we can just create the work plane. So for work plane, we have to go to the surface. In surface, we can create the plane. So plane will be created at the bottom like this. And now to find out the proper size of this plane, we may create a bounding box around it. So how to do so? We'll select the model, we'll right click on it, and we'll go to the selection information. So here you can see what is the minimum, maximum sizes like in X, Y, Z. It's all are shown over here. So basically we need only X and Y. So from there you can directly get the direct output of that length, and that directly you can set in the uh, plane basically. So I'll click the plane, and in the plane we can define maybe it is like 100, maybe 100 by 100. Sorry, I just selected the cone again. We'll create the plane, then yeah, we'll just define it to be like 150 by 150. Just always just make sure it like the entire part is kept inside this sizing plane. So that's why I kept the clearance of 5 mm. Then once it is done, now we are going to move this one by the layer height. Say suppose maybe 5 mm. Then we are going to take the intersection between this plane and the curve. So since it is an 2D operation, we will find in the 2D tab. So in this power set, basically it comes at wireframe. So under wireframe, you can see this intersection curve. Once you select it, first you have to select the first model, and then you select the slicing plane, and then click OK. So now I got the slice. So I will hide the model. So you can see this is my slice curve. So now I'm going to offset it by the machining allowance if required. So I Yeah, okay. Then yes. So yeah. So here you can specify the starting point, angle and all. Then limit okay. Then your tool axis you can specify over here. Then you can redistribute the points if it is required. Then step over you can define over here. Whatever if is set over you're obtaining from the single bit experiment. Then here we have the rapid height. So rapid height is nothing from which height it will coming. So it maybe keep it like very low to save the time machining excess machining time. You can keep it very low. And all right. So right now it's creating along the boundary. Okay. All right. So there is some issue. I'll just check it. Yeah. Maybe we can just specify these things again. Mm, yeah. So again, I will remove the boundary. So now it's saying, so you can see that it's created an entire thing. The pattern is getting also because the pattern was in a wrong position. So I'll delete and recreate the again pattern. Uh, to switch off the toolpath view, you can just click on this bulb or you can either deactivate it. And now if I select this curve, variable block also I can hide from here. And then we create a pattern and insert this curve into the this pattern. And now if you copy this pattern and paste as the boundary, now if you go back to this toolpath and you define this boundary over here and click calculate. So you can see the toolpath has been created inside this one. So I hope up to this clear. So once you get then you can simulate over here, go to simulate and you can click over here and you can just play around and check whether it's going perfectly fine or not. And in complex shapes like in repair, there might be some protrusion next to this contour. So you can also cross check whether it's having some collision with that person or not. So these things you can do over here. Then once it is done, then next thing is like create the NC file. So for creating NC file, you have to right click on it and you can go to the create individual NC program. Once you go to the NC file plus, then you right click over here and go to settings. Then you can define the toolpath name. Say suppose toolpath maybe 2, layer 2 maybe. Then you can specify which folder you want to store it. Maybe the desktop. Uh, then you have to specify the machine option file. That is nothing but your controller. So like I said, every controller accepts a particular file extension. So maybe you can select Fanuc one and click accept. And then you can select the output work plan because if you're doing 3+2 deposition, like you index to certain position and then about that on there only you can want to deposit that three axis strategy, then in this case you have to select the output work plan about which you want to generate the NC file. So you can select from here, then you just like click on the apply and click on the right. So it will generate the toolpath. And yeah, again if you go back to the desktop, the toolpath 2, if I right click and open with maybe SimCon notepad also, then you can see this toolpath. You can see it's having all the G codes and M codes. So now the next step is like before G01, we need to put the welding on command. 137. So herely I can write maybe at the beginning of 137, maybe once it reaches over here, I can write M51. So which is going to start the welding. And then I will keep on searching for the next Z00. So here Z0 is here only. So before that one, I can put another command of maybe M52. And then I can just save it and just directly you can take this file and put in the CNC machine to deposit it. So here you can just when you can check the backplot also, like how it's going to move. So you can see it's at which point how it's going, and everything can just verify over here once again. And then finally you can take this from file and you are just taking to the machine and you can just start depositing using the same code. I just like to highlight once again this M50 and M50 is nothing but the welding start and welding stop command. So basically we need to we are controlling the deposition process with the help of the NC file, M code basically. And to do so, we need to take out the two terminals from the welding source, power source, trigger source basically. Then we need to connect it to some solenoid and which are connected to the PLC of the CNC machine. So whenever we give some sort of M code defined by the logic ladder diagram, then it will automatically back to you. I won't save everything. Then I go back over here. So this is for one basically one slice. So if you want to do that for the remaining slice, one way is like you can keep on doing this thing again and again. Like again you come back over here, unblank, and then again you just move the slicing plane by the layer thickness, maybe 5 mm. Then again repeat the same thing. One way is this one, or another way is like we can write a macro, basically API, the one I'm showing at the beginning. So to do so, you can go to the home. You can see this option called macro. It is well common in Microsoft Excel as well. Like suppose you're depositing, or maybe you are doing something again and again, like calculating the marks or percentage or grade for the PCM or NCM, something like that. There also we use this kind of functions in the Excel, and thus you can write in a macro. So a similar way here also you can write a macro. So one way is like we can directly run start recording the macro recording. You can start from here. So you can go to the desktop maybe, and I will write maybe one and save. Now whatever I will do now, those commands will be stored over there. So maybe I want to move it. So I will select on this one, edit, move, and maybe by Z height and click OK. And then I just stop this macro. So if I go back to the menu, then if you click over here, so you can actually see some sort of commands basically. So you can see edge surface, then edit move, Z5, apply dismiss. So this is the basically command. So if I select this instead of Z surface 4, if I select like surface 1, 2, 3, 4, 5, those surface I've already created at the beginning. And then or maybe the first surface I selected, and I keep on adding in a loop inside this loop only this Z5, and within this loop if I write the intersection command as well, then I can make the entire process automated. And if you want to see the command for this thing, so you can go to maybe user interface and you can open the command window, and right now I can see nothing is there. So if I do some sort of operation, it will pop up over here. Say suppose intersection curve. So you can see it's saying like enter the offset thickness and sorry, select the oh sorry, I selected offset. So it's an intersection curve. First one, this one. The second one is this one. I click OK. So these commands you can actually check in this command window. You can select option accept or not, the construction method, then accept OK. So if I blank this one, so you can see this curve has been created. So in this way, you can get the commands corresponding to intersection. And another way is like you can just record the macro for particular operation, and then you can just open it in notepad and check it whether it is fine or not, like it is the same or not. So this is the one thing. And yeah, then this is Okay, fine. And then next thing is like similar way we can do over here also. Say suppose if we want to record the commands for this for power mill also. Here also we can just there's some examples are there. We can write over here. We can right click and start record something like this. You can just do over here also. And if you want to see the command window, so here also it's possible to see the command window. So you can see whatever operation you have select done, it's been already written the corresponding commands over here. So those commands you can directly copy and write a single macro, and then we can just make it automated one. Like we can put in a loop, whatever files comes, just report these things and rotate the angle by 35 degrees or something like that. So those automation is possible with the help of this macro. I hope it's clear to you till here. So next thing is like so that we have already done it. So I will show you one example. Maybe I'll just close this one. No. Okay, yeah, I will just close this one as well. So we'll start a new model and I'll create the workflow at the global origin. So we'll create the workflow at the origin. And now maybe I'm creating one model, maybe something like a spare maybe. Yeah. So now I can create another workflow in the bottom of it, which will help us in generating the slicing plane. So select it and create a workflow at the bottom. All right. So now we have developed in IIT Guwahati this same software like using macro only. So you can see here you can define the layer thickness, maybe 2. Then machining allowance you can specify over here. And then this is step over you can mention maybe to be like 3 mm. Then you can set the deposition speed. So maybe 1000. Then you can select the tool path. So here you can see you're using the direction parallel, which is nothing but a zigzag only, but zigzag with minimum lift. So we have put some own logics so that we'll calculate whether the number of lift is optimized or not. If it is having more number of lifts, then we're going to rotate the zigzag angle in such a way that until and unless we are not getting the minimum number of lift. So like that, we can just specify over here. Then you can see you can write over this 3-axis slicing. We just click on the 3-axis slicing. So that one is selected. Now it's automatically creating the slices. So I'm not doing anything. My just hands are out. So this is automatically by this cam only. That basically this macro only. So all the slices are being generated. So not only generating, and one thing that in the previous session I just showed that towards the end that because of the lower number of point the slice control, it creates issue during toolpath generation. So to eliminate that thing, we are just repointing, like we're selecting the slice and increasing the number of points in this curve, so that no such issues will be there in the power mill basically. And yeah, it's showing how many total layers will be required, like 21 layers. And to automate how many layers it will be required. So you can do one more thing also, like you did during recording the macro, you can select the model and you can select the bounding box. And is as you know from the bounding box, what is the maximum jet height? And also you know about this jet height and you know the layer thickness. So from there you can actually calculate how many layers will be required. And even you can put some other information as well, extra some other information as well. Like you can calculate the volume of the part to be printed. From there, by just by multiplying the density, you can just also show the prediction how much material you will be required to print, will require to print this part, something like that. So this is also possible with the album macro. And we have put the condition such a way that this will keep going until and unless when the intersection between this plane and the model is none, like it's zero, nothing is there, then it will stop. So now it shows that it's already done, slicing is done. I click OK. You can see slicing is completed. Next step is like I need to generate the tool path. So for that, I just need to click on this 3-axis tool path. Just click 3-axis. It will just give one error alarm that all the entities that are already being open in the Power Mill will be deleted. Just click OK. So now you can see it's just popping up this between these two windows. Basically, it's just transferring the layers one by one and it's creating the tool path, tools, and it's generating a tool path over here. You can see you don't need to do anything. All are done by this macro. So only thing we need to do is like you have to put in the loop only. So now you can see over it's showing that it's just generating the NC file. So then transferring data, one is completed, then two is going on. So like that, the entire model will be completed. So sometimes it take some time depending upon how big your model is and how complex steps you have. So if you go back to again Power Mill, you can see it's just following all the steps that you are doing. So you can see up to 5 it's written. And once the data is used, then they just delete the slice information and come back to the main. I hope it's clear till here. And yeah, even you can see define toolpaths also is here. Like you can select this Hilbert piano curve. Then even there's an option called fixed angle. Like suppose someone want to print the entire part in a single angle only, that you can fix over here. Even you have some contour pedal toolpaths. So not only this, even you can try your own also if you have some own toolpaths. So those coordinates you can import. You can create one tab over here where you can import just or maybe copy and paste all the coordinates of your trajectory. Then it will this software automatically convert those trajectory into G code and M code, which finally you can take an USB stick and put in the machine and get it done in the printing can be done over here. And yeah, so it's on 14 layer is done. So if you come back to Power Mill, you can see it is already generated the NC file as well. You can see like up to 15 layer NC file has been generated. So right now we are generating separately, but it is also possible to generate a single NC file also so that we can directly put uh, in the machine and in a single go only you can print the entire part. So it's writing again. Eighteen there, 19, yeah. And finally 20. Okay, it's showing that the toolpath is completed. So now if I go back to Power Mill and if you switch on all the toolpaths, then you will be able to see it. So you can see this is the part. So and corresponding toolpath, the NC file with the corresponding toolpaths are written over here. So each file are written. You can just download these files and directly put in the machine to get the final component printed. So this is here like till like mostly for 3-axis strategy. But if you want to make some overhang structure, like maybe this spare only. First I'll exit this one. yeah, so I will come back to here. So once this toolpath is done for the deposition, next I can generate toolpath for milling as well. Because like I showed before, extruding the offset contours. So based on the offset model, we can just generate machining toolpath for getting the final finishing shape. So this is possible over here. So since I don't want to machine, then it's fine. They can just directly exit from here. So now again, I will just delete everything and maybe just create new one. And again, if you create a work plane at maybe origin, and then you'll put one maybe same spare maybe, or maybe torus. We can try with torus. Let's define the diameter to be 100 and 30. All right. So suppose I want to deploy this part. So if you observe, this is nothing but an overhang. So how to encounter this thing? So one way is like I have to tilt the position. I have to tilt the this either bed or a deposition in such a way that a gravity comes in this direction, in this tangent direction. To do so, first we have to we propose one method called double slicing. Maybe I'll just go over here. Let's get one uh, work plane, slicing plane over here. First work plane will create at the bottom, then we'll create one slicing plane over here. So let's define this width and breadth to be like around maybe 300 by 300. So uh, click OK, and now I'm going to move this by. So maybe this is my slicing height, and just to define its angle, we can get another slice at just above it. So we can do it move, copy one, and very small distance above it. We can just do it. Maybe I will just for clarity, I will take one now. Okay. So now you can see say the interest. Now we just set this. So there is just uh, see get two curves. It's having an angle. Now if I define my curve in such my torus follows this curve and follows this, then I can be able to deposit something at an angle. So similarly, we can just transfer this to the our power mill. We'll just bring this one. Okay, just okay. Now if we take this all data to this power mill, okay, it's already open. So maybe I'll just close and start. We'll select this one and we can just go to the power mill. So now you can see there's two curves are there. So maybe I'll just hide the slicing plane. Now first maybe selecting maybe one curve and inserting as a create pattern. and inserting as one model. Then we create a second pattern in which I'm going to put the bottom curve. Yeah. So now one thing we can a similar way we can maybe put the curves for the other two curves, but let's focus on this one not maybe. Now if you go to toolpath again, maybe one and this maybe five and keep on and thus okay, maybe it's just 30 and the block, and now it's not visible because I switch off this view so I can see over here and give accept. And next we will have to create the toolpath. Go to create toolpath, then go to finishing. In finishing, if you go to one strategy called pattern finishing, if you select it and click OK, now in the pattern you can select maybe one curve and yeah. So and we'll just select one by one. Work plane. Then you can click the block. Already created, tool is created. Limit is like not required currently. Then pattern is there. Then tool axis you can instead of having vertical, we can put from line, from curve. So here you can select this curve 2, and then the remaining height we can specify. Since you can see over here, the tool is going inside this material part because it's the rapid height is quite low. We can put it maybe a little bit high. And rest we can just click calculate. So if you simulate this part, so you can say it's going at an angle. And this angle is nothing but the curvature angle only. So this helps in making some overhang structure without any fall down, any support. And since this is relative motion, if you're using a turntable table, it will just allow to make this this curve quite easily. Once we cut the outer contour, in infill we can go with then there is no boundary around it, so it would have to fall down. But now it has been restricted by this pass. So this will help to store the material inside this say hole, and then other way like it will just go with this one. So maybe we can just delete everything or create a new one. And work plane, okay, you can create the 0. And then maybe if you create some this same torus only. Also delete one. Okay, it's there. Okay, we're just getting the one torus. And if you specify the dimensions, maybe like 100 and 30, and Yeah, okay, it's done. So next thing is like we just select a model and we'll go to this again this GUI that I've created over here. So here now if you select remaining parameter as same only, and if you select this as 5 axis slicing and you just check this one. So yeah, before that one actually it always asks to save the model. So we'll just save it up maybe desktop. Now showing once already selected, click OK. Now now we'll do the 5 axis slicing. So the layer height is quite low, so it's just creating multiple slices. You can see it's as per the number of layers, you can see different levels have been created. So the best thing is this one, like with any overhang, we can just simply create it. And because if you since you're depositing the inner area field with the fixed strategy, so calculation is not taking that much time because the most of the time is taken the depositing the outer contour only. And there also this contour is giving multi-axis we are using it. So there is no issue of any material dripping or anything like that. And the overhang angle right now we are specifying, but whatever overhang will come, like even 90-degree overhang also is possible to deploy with this strategy. So it's taking lots of time. Maybe I will just stop in between and because it will take lots of time. So I'll just stop it. Okay, it's not taking command. So anyhow, so like this only, this strategy actually used to define the tool axis. The another curve is the normal slicing curve along inside which we're going to deposit the material. So okay, so it's just going on. Uh, I think it will take time, so I will just scale it up. So okay, we just hanged actually. So all right. So by the time it is fixed, so I'll just show you the same thing we can see in the solid rocks. It is being used. So if you go to the sketch and go to the convert entity, insert this one, you can see this intersection curve. The same tool that I've shown you in Power Shape inside this wireframe tab only. So same thing you can use over here. Switch it off. Okay, again I'll just launch Power Shape. So I'll just close this one as well. So this is what called double slicing basically. Okay, go back to few slides over here. So I hope it's clear to you how it works. Like first, to import the model, we create a slicing plane, then we take the intersection, then as per the machining elements, we just offset the curves, and then we just deposit as per this offset curve. Then we generate a face milling toolpath for this if required. Then these extruded curves are then so offset curves are then extruded, and the slicing plane is moved by the layer height. Now this slicing plane is again this process is repeated, intersection between the slicing plane and the CAD model. And the same thing is repeated until and unless the intersection between the slicing plane and the model is null, which is 0. And this extra model is down, then exported to power mill, and it is used as the raw stock for the final finish milling, just to avoid the unnecessary air passes. Then all the deposition toolpaths along with the finishing toolpath are post-processed and generated as G code, which has been then finally fed into the machine as per the controller, and it just put in the machine and the machine just prints the part finally. And this is the final shape, and this is the scan model. So we have already tested it: power shape, power mill, master again, camworks, and then NXCam. So just to compare these things only, that the part we have printed, the deviation is like only 40 micron, but it's quite acceptable. So, if you like, I just showed you that multi-axis strategy. So that is only used when you go for some higher kinematics machine, just like 5-axis CNC machine or maybe a robotic one. So for robotic one, like I said, the robot also we need to program. So for teaching or the programming robot, we have two modes. One is your online programming, or one is your offline programming. In online programming, one is like using a team, just to the position of the robot and just into the next position, and you keep on collecting the data of the contour, and then you can automate it. Just once you play the cycle start, and it will automatically move along the path that you have been trained. Second method is like your lead through, in which basically we hold the in effect of the robot and manually move it along a path, and at each point we are going to store this data. So now the robot will collect this memory, and whenever you run the cycle start, it will automatically follow that particular path only. So this lead through is not a good idea when you are dealing with some heavy robots, something like maybe R2000 Fanuc, which a payload of 210 kg. And teach pendant programming also is good only for simple structures, but if you want to do some area filling, some 3D components, then it is also not a good idea. And the last option that left is that this offline programming. So offline programming is like you can directly generate toolpath using a virtual environment shell, and where you program it, you take the data and then come back to the machine and just put in the machine, and the robot will start working. So that's why offline is much more preferred, because you don't need to interrupt the robot. Like in case of online programming, you need to go to the robot to stop the robot, and basically you you have to store all the data and points, and then it's programmed like that. So that's why for remote you have to always go with the online programming. So in Parallel also it's possible. Like you can see over here, it's a defined user toolpath. We call it a TSP toolpath, travel specific toolpath, in which the entire area is filled in a single go. And this kind of user-defined toolpath you can easily import into this Parallel software, and you can just convert those data into a robot program, because this robots works in the principle of inverse kinematics. For at each point, say you have to calculate the corresponding joint angle. And it is not a good idea to calculate it manually because certain complex shapes, like in this case, there are more than 10,000 to 20,000 points in this part. So for calculating angle for each point, it will be like so much tedious work. So that's why we need to rely on certain software such like this robot plugin, something like that. And even we need to define the modify the post processor as well. Like wherever there is a like cutting move, like the feed move, there we can just put one line, and we can just put the command for well done command. And even when you as well. And similarly, at the end of this deposition toolbar, you can put some automatic command to stop the deposition. Say like suppose just like M52, you can write a will stop or whatever command the robot follows, that we can put it. And since it's a already well established CAM software, so we can use it for any other non-standard robot as well. Suppose you have some own robot that can also be created over here, and we can just deposit in the same robot as well. So I will just show you how this actually works with the help of this robotic arm only. So first we'll create the work plane maybe at the 0. Then we can create the maybe the cone again. Okay. So this time we'll keep it a bit smaller one, maybe 30, and 10 is okay, fine. All right. So now we select this model, and we like create this toolbar. We specify, we'll keep everything as it is, whatever it is. The step forward, we'll just reduce it, maybe increase it, maybe the 500, and bit 2 is fine. Then we'll go for this direction parallel with minimum lift. Then we're going to create the 5-axis slice. Once I click over here, it will ask to save the model. We'll save the desktop. So now once already selected, click OK. Now we can just click on the 5-axis slice. So you can see it's just creating all the points. Since it involves generation of different points and repointing again and again, so it takes longer time than other toolpath generations. So if you observe here, you can see every slice, there's another slice corresponding to each slice. And these are like the other thing. Okay. So it's hit okay. Now if I go back and it's doing this overhang treatment, like it's just checking wherever it's required, there only it's generating this tilt angle. So once it is done, then we can directly go back to the Power Mill to generate the tool paths. So in Power Mill, there's an option called this particle plugin where you can select different robots are there, and even the standards ABB, KUKA, Fanuc. So all this can you click OK and you go back over here. And now if I generate in 5 axis toolpath planning and click OK, it will just start from the scrap again. It's just working over there. So it's generating. So you can see how many points has been increased. Because if the number of points are less in this curve, then when you generate the toolpath, it will oscillate a lot because it's going to only tool axis is only going to calculate for its corresponding points. So for smooth transition of these passes, we need to increase the number of points in these slices. The same thing we have observed at the beginning as well. So it's going on just it's also writing the same time that NC file. So because I clicked that time some wrong in between, so this one random slice comes this one. So you know that you can ignore it because our focus is like how it works that you can observe from these other slices as well. I hope till here it's clear to you like how this multi-axis slicing works. So once it is done, then we'll show how to import a robot and all. And like I said, it's going to only generate the tilt angle only for the outer contour. For inner, it will be anyhow going to generate for the normal slicing, the normal 3 axis deposition only. So it's showing like toolpath generation is completed. Now I'll come back over here and maybe I will activate maybe toolpath one maybe. So you can see if I run this one, you can see it's just printing like this. If I click it done, then you can go to beginning and you play it. So you can see as per the angle, it's just depositing. Now suppose I want to convert this toolpath for robot. Then what I need to do, you can just go to this vertical plugin window with this bar mill. So there you can see lots of standard robots are there. So based on the robot that is selected, not only depend, you can use some non-standard toolpath as well. Standard robot as well. Like you can say, there's a Panasonic robot is there, so you can select it and click double click. It will just pop up the robot over here. So this is a non-standard one, so we have imported by ourselves. So when you can use your own robots also as per your requirement. So then next step is like you have to go to robotic cell. So here we need to define the position of the part in the actual cell. So you will click over here, and if you go to robot convention, then you can just specify where your part is as per your robot world coordinate system. The robot world coordinate system is defined for defined robot. For most of the robot, it lies at the intersection of J1 axis and J2 axis. So and similarly, there are certain robots like ABB where the origin lies at the base, like intersection between the base and the J1 axis. So accordingly, whatever robot you have them, according to that world frame, you can just put the part over here in the cell position, and okay, you can maybe increase further and 50. So you can see over here the part will be offset over here. So click close. So okay, I will just switch on the. Okay, fine. So now I have put up position like my part will be lying somewhere over here. So these coordinates is can be also retrieved from the actual robotic cell. I can take the robot to that position and I can store the XYZ coordinates and WPY coordinates, and same I can bring over here and put at this place, and then I can set the state origin. Once it is done, then next thing is like you have to select the post processor. So for that you need to go to the robot configuration tab. So there we can see define information of the robot like where the head is attached and what are the work planes, home positions, everything you can check over here. Even you can select the inverse kinetic solver as well. This is a standard inverse kinetic solver. Suppose in your case you're not able to generate the unique solution for the robot, then you may actually switch between this inverse kinetic solver and then I can start again solving. This is one way. And finally, the important thing that you need to set over here is that post processor. So as per your welding machine, you can choose the post processor over here and then click save. Then next thing is like you can go to this control tab, and if you right now you can see all these tabs are disabled. This is because we have not activated any toolpath. So let's activate one of the toolpath. And now if I go to back and if you just click on the play, so you're able to visualize how it's going to move. So you can see the angle in certain cases it's showing the error. So these kind of things you can actually predict it before going to the machine. So you can see these two axes already reached the limit. So that's why it's showing the error. So if you save this project, yeah. Once you save this project, then you can really save the simulation. But right now it's showing there is an issue. It is because that angle is actually limited. So you can see some orientation factors are not able to save. So hence the next thing is like because we have kept it too much close. Maybe if you keep it little far, then it will be quite easy. Or maybe I will show this thing with the help of maybe some other robots that will give you better idea how it actually working. Maybe Fanuc, okay, with this one we'll try. So he can put the part over here. Then if you go again, start simulating this one. Take it. This one is wrong. Again, we'll put. Yeah, all right. So it's just showing collision because the gap is too much low. So if we increase the Z height maybe over here, then you can actually see how it's going to work. This is the case only. We have the substrate at the bottom. So anyhow, we need Z height for work properly fine. So now if you run the simulation, again still it's showing the collision. So we just need to increase it more, and then it will be perfectly fine. So like these things, like now we know the position. So in such position, same position, you can again go to the robot and put over there. So this helps in avoiding accidents and all before going to the robot. Go back again and just rerun this simulation again. And now you can see there is no collision. And even you can now this E1 is static. So you can maybe since the change this axis also. Now if I play it, see when at the same time it's turning the bed as well. And turning in such a way that it can easily solve the solution, something like that. So it's possible. But programming this kind of kinematics manually is not a good idea. So again, it's showing some error, but it's fine for the demonstration. It's okay only. So you click OK. You can see there's showing a re-singularity. So there is option for avoiding re-singularity also. If it enable it and rerun again, so like this, you can just identify all the errors if anything is there. Once it is done, then you can just go to this robot programming menu. So here you can just specify the file name. Then maybe you can define the output frame. Like this is the just like the work offset, whatever work offset you are setting in the CNC place. Similar way you can set over the robot as well. And then if you right click over here and you can select the tool path, and if you define a tool, then you can actually write the tool path over here. And once it is done, then it will show you the code file. And if you open it, you can see all these commands, how it goes. Coordinates the orientation of each point as per their end effector. It will be stated over here. So like this, you can create toolpath for robots, and just you can directly take to the robot and you can start printing on it. And we can even put our own robot, like I said, and yeah, you can define this axis. And not only that, even you can develop your own robots, and the controller might be of your own. For same also, you can generate a force processor from here only. So I hope this is clear to you how to generate toolpaths for robots. And in similar, we have demonstrated over here. Okay, yeah. So in a similar way here we have demonstrated like some user-defined toolpaths were created over here and it's working fine. And you can see this one over here and the same thing reporting over here. And even we have done some complex AI contours also like this one. And not only this, even with this developed framework, like you said, you have much more flexibility in selecting the slicing plane and all. Hence, we can go maybe much complex shape as well. One is like maybe slicing, like if there's some overhang is there, it's like we is a undercut. So like you can see in this case, but this is not enough for handling overhang of a certain angle. Therefore, traditionally, people go like slicing, multi slicing. Like first they'll go with the horizontal slicing for a particular part. They will go another horizontal slicing in a different angle direction, like you can see over here. But in this case, like if you see from here, the distance from this base to the slicing plane is equal at some tangent position only. Once you move away from the tangent, the slicing thickness will vary, and that is very difficult to encounter accumulate. You make some therefore the best way is to using some conformal slicing strategy, or in other words you can call it non-planar slicing. Like if you observe in nature, all the things grows conformally. Like you can say these things, like you can see it's from the core it starts growing like this. Even this one also growing like this, cabbage also growing like this. So in the banana triangle also you can see like this layer. So in nature everything grows conformally. So inspired from this one, we can make any such part using conformal slicing also. Like you can see this part, the bottom this one, it's doesn't have any overhang, so you can really slice it using horizontal slicing. Then for these protrusions, we can use we are going to use the conformal slicing strategy. So basically, we're going to use the slicing plane conformal to this plane. Then we're going to keep on offsetting until it covers the all the protrusions around the part. And then you can take the intersection between this slicing plane and this model, which will give you this kind of slices. Once you get a slice, then we can implement some non a non-planar toolpath planning, or maybe something like that, multi-axis stability. Such kind of strategy we can adopt it, deposit inside this part. And sometimes it is required, like not can I say like you have to every time you have to go with the conformal. We can do some hybrid also. Like I said, suppose in this case, it identify the portion which is not having any overhang, like this portion, that we can directly select the horizontal one, and that can be identified just by multiplying the summation of curve of this vertex with the bit size array secant. So if the dot product between these two is less than this means this is overhang, and if it is not, it is normal. So if it is normal, we'll go with horizontal slicing, or if it is overhang, then first we'll create the slicing plane conformal to this base. Then this conformal plane is now grown radially, like you can see over here, and now we give us this kind of slices. So and you can see over here also. So right now the middle portion we are depositing in normal 3-axis strategy. Now for depositing the overhang, we have tilted it. And if you closely observe, even in this image also, this plane is conformal to the base. So distance of each point from the surface is actually constant, which helps us in getting an uniform layer thickness in the conformal layers. And yeah, then this another benefit is like you don't need to alter the deposition parameter during this deposition of this layer, because if the layer height is varying, so ideally you should vary this welding current as well, but in this case it's not required. And yeah, this you can see at each point XYZ, all the coordinates are varying in this case. So this is all about conformal slicing. So now we have implemented these strategies in different WAM systems, one industrial case studies. One is there is a variable transmission housing. So this is for a New Zealand-based company. So we have printed using the same framework that we have already shown to you. So ideally, it was making using conventional machining. The cost was the wastage was coming like around 14 kg. So then we propose to use the WAM. So in the WAM, you can see we can reduce the wastage till 1 kg. Like you can see, if you make this part in this way, the in 3-axis strategy, then inner portion will be the waste, like this portion. It's coming to 1.9 kg. But if you make the part in this way, then we can reduce the wastage till 1 kg. And once it is done, then we can do machining on it, making a hybrid process, and finally we can get the final component, something like this. And this is the final part. The height is like around 100 mm, and the material is aluminum. As you know, aluminum welding of aluminum is quite difficult, so it's only going with the CMT or maybe AC power. And we have already tested, assembled and tested, and it's working perfectly fine. And already there are another study is going on in IIT Kanpur for that company. And yeah, and so more access then casting also expensive. So in this case, actually, this one was proven to be much more cheaper option for that company. Then another things we have printed is like for some aerospace industry, just thruster of a rocket engine. So earlier they are making it out by using powder bed fusion. So they are actually creating lots of issues, like wastage was not wastage, cost was quite huge, and it is like and they are paying like around 4 lakhs to print a single part. But in WAM, we have proven that we only cost is like around 1 lakh. So plus whatever head we have to consider, so we can actually reduce it. The novelty over here is it's the Inconel. The Inconel is having very much low conductivity, hence it stores the heat. Because of which material drips up at the end. So to avoid that thing, we have come up with a new tool path. Like I can see over here, it's a discontinuous tool path where transfer material drop by drop, and in this manner we're making this kind of structures. And you can see we have compared the cloud data also. So we have anyhow excess material than the required one, and it directly you can just machine it if you require a good better surface finish. So you can see over here how it's all the plannings are there and how it's going. This is the simulation video and this is the actual video. This is simulation and this is actual. So all these things you can incorporate in the existing CAM software only if you do some tweaking with this macro and API. Then another case studies that we have done is like we have fabricated some camera housing for some underwater remotely operated vehicle. So and they have already tested this performance this part for underwater application up to a pressure of 20 bar, and it was totally leak-proof, no crack was developed. So this is also the case study for WAM. And then another thing we have done is for the for industry mining industry where they are using this kind of status. So the challenge over here is like depositing such thin short passes, because these short passes is like if you deposit continuously, it will start dripping at the end. So therefore, we are transferring material here drop by drop. Hence, we can go very thin features as well, thin length as well. So here we just gone like this, and we're able to handle the heat accumulation as well, because we're depositing one drop over here, then next drop over here, next here, like this. This helps in cooling this person away at a faster rate till it reaches back to over here. Hence, there is no issue of overheating and dripping of material at the height as well. So you printed the entire part and already able to that industry, and that industry earlier they are making it by welding. They cut these plates to welding over here, so it is taking like around 12 hours to make one part. But with this additive manufacturing, we have proposed them to that we can make this part in 8 hours only. There's 4 hours reduction in the build time, and there is no human intervention. Like here, you can directly just put the machine, start the machine, and go away. So you can get the entire part over here. So this computer processing for this tool part also we have developed on top of this Power Mill Power Shape only, and same you to use it for SolidWorks as well. Then different automotive parts also are printed. Like you can see, these kind of organic structures were quite easily printed using this three-axis strategy only, but with this drop-on demand strategy. Then some bearing cases for heavy equipment, and after machining you can get the final shape. So you can see it. So we are depositing over here. So basically, we can say we can print at zero. So like the quite easily printing without requirement of any support structure. It just inspired from nature, because in nature all these things grows like drop by drop. In similar way, we're just creating over here only. Then another application, potential application of this software, like you can use it in repair work as well. So here initially we need just like discuss at the beginning of the session. We do some single bit and multi-bit analysis. So we to study those single bit and multi-bit analysis for different set of materials, say stainless steel, steel, or maybe stainless steel nails, to study the single bit experiments. Once you satisfy the parameters, like whichever parameter given the best solution, like best penetration and best over contact angle. So those we are going to use it to repair that kind of owner components. So that's also using the same thing. Thus we just scan this portion. Then on the scan portion, we have this uh, defects are identified. So wherever defect is there, we're going to just generate a surface normal, and along this surface normal, we move the torch, and like that we can repair this mining equipment. Then another application that we can use it for like density based FGM, like we can make some monomaterial density FGM by hybrid process. Like you can deposit the layer, then you can use the drilling machine. Since you're using a hybrid worm, like in a mounted on a CNC machine, so well, you can quite easily machine it and vary the density by drilling the holes inside it. And not only that, when we can just um, deposit the we just create these holes in such a way that we can obtain a particular density gradient. And the principle is quite simple. We're going to generate lots of points inside this contour, and now we're going to form dynamic triangulation. It's self-connecting all 3 points to forming one single triangle. Now, if you do the force balance, by treating all these points as mass and all the edge of this triangle as the spring, and considering the stiffness to be similar, and if you apply a force balance, all the points will come at equidistance. Now, if you apply the new force on it, then it will distribute as per a new force, which is nothing but a new density function for that given layer. In that way, we can do it, and we can actually achieve the density function. And these points nothing but the position of the holes. So in the same framework that I have shown you few minutes back. So in the same framework, we can uh, able to print any density based component as well. And since a hybrid process, so software is also for hybrid process, so we can easily in a single program file only we can generate this kind of full parts. So this is just to demonstrate, like even from the image also you can create such whole position and all. And this time we can also analyze the figure out which is the base hole, so that the materials should not flow inside it. Then this analysis we can perform to figure out the base hole diameter and hole spacing. And the quite major advantage of this process is like you can see we can reduce the mass like around 8%, and even you can reduce the conductivity as well, because since these holes are having nothing, like it has the air and depth, so those acts the insulating material. Hence, the conductivity has been reduced by 26%. Even you can reduce further if you again increase the number of holes in this part. You can reduce further, and even you can increase this conductivity of the component as well. Uh, Eventually, it will have another advantage like the stresses and all. So these kind of things we can explain with this framework. Like you can see, it's an intermediate layer. So you can see the holes are not uniform. It's like more hole over here, less hole was there. So these kind of things can create over here. And runner to like the sort that so it has um, like people might argue that it might have some effect on material properties, but that is has been wrong. You can say over here that the tensile strength and all are same in all the 3 directions. Then since we are waiting in between the two drops, hence the we can get much cooler cooled deposition like profile over here. And yeah, and if we can compare the continuous position, you can see there's much more warpage because of continuous position. But with this kind of new strategies, we can reduce the this warpage as well. Even you can come up with some other ideas also. Like you start maybe right now we're going continuous. We can some ordered way, which may even reduce warpage also, further reduce warpage. So these kind of new strategies, new based toolbars can using like existing CAM software. And it's just an example how precise deposition we can make, how like horizontal depositions. Then this kind of wiring structure you can easily print with the structure. So all these things are can be done using the same framework only. And then other things is like you can even use for repairing of holes, and programming of such thing using the robots. It will be much more easier if you use Power Means this kind of softwares like or maybe you can develop something your own your robot solver. So that will be also useful for making such kind of API applications. And yeah, then there are certain materials which actually develop cracks, cold cracks after some time. So like this is the case of Windows kernel. So but wasn't this so this kind of things so it's possible to achieve with the new business novel strategy I can explain. So so far we have learned about this experiments, how to do the experiment like from the beginning, single bit, multi-bit, multi-layer. Then we have used those data to for the CFD process, like slicing and toolpath planning and all. Now, suppose if you want to develop some numerical simulation of the swarm, that is also possible. And there are many commercial packages there, such as like Abacus, ANSYS, 3D. Recently, one Indian company is also there, like some Pandu, something like that. So Prabha, something like that. So there are many softwares are there, and most of the software these days come up with some add-ins where you can directly simulate the editing process only, the welding process only, similar to Simufacts or Simulate software. So here I'll just briefly show you how you can develop some numerical simulation of warmth. So for this one, first basically you have to develop the CAD model of it. Once you develop the CAD model, then you import into the FAQs, design along with the bead, and then you have to import the material properties. So the material property, if you are using some constant material property, that might lead to give you some wrong results because there are certain properties those varies along with the temperatures. Same as like some surface sensor maybe. So varies with the temperature. So those temperature dependent properties you have to put at this beginning. And then since it's a software, it's a partial environment, so it doesn't know where the part is. For the software, it's like it's in the air or maybe it's floating in the space. So to tell it that it's lying in welding bed or basically welding table, we can just need to put certain boundary conditions. So for one, we can define some another material over here and define the properties of the bottom plate as the properties of the other plate of the welding bed. Another way is like we can directly use this model and we can put the convection heat transfer coefficient as I, so that those represents as a conduction only. Like at the bottom plate, I'm going to put the convection too much high, like maybe 400, 500, something like that, similar to the conductivity of the material. And then for the edges, if you observe, all the walls will lose the material by convection and radiation. So accordingly, we're going to put the properties around this walls. And finally, we need to apply the thermal loading at that bead center point. So suppose this one. So applying thermal load, we need to use subroutine Avegas. So this is a thermal loading condition. Basically, we consider the heat source to be double ellipse saddle. This is because when you deposit in a basically layer, or basically in a substrate, single bit experiment also, you can observe some tail in the main tool. So from there only this concept comes of double ellipse saddle. Basically, if you observe from the top, it is actually formed using two ellipses. One is this bigger ellipse and another smaller ellipse. By combining these two ellipses, you can get this model of heat surface, double ellipse saddle model, and is developed by Goldak. So if you consider the focus of the front uh, ellipse as the origin and the minor axis is the y-axis and x-axis, then we can get certain parameters of this middle pool. So by like A, B, and all these things. So by defining these things, uh, we can get the heat at the front and the rear. This is because the heat concentration is quite high at the beginning because it's coming directly into the picture of the arc, and when it's moving in the forward direction, the rear end of the heat source have a little bit lesser defined heat energy. You can use this kind of uh, this equation basically. And just to consider a factor, we use this front FR and FF basically. So nothing but heat equation factor only. Then once we get thermal loading, the next thing we need to do is like meshing. So meshing is nothing once this is done, then we can directly run the simulation. Like you can see the heat source is moving from here to here, and the tail is from at the end. So you can see over here also. This looks like this. Even in actual welding also, you can see the tails behind the main pool. So this is nothing but evolutional heat source. For writing the user subroutine, so you have to go to load, and if you go to edit load, there you can select the distribution user define, and there you can select this particular Fortran code, basically subroutine only, written using in Fortran language. So you can see over here, like or you can define all the parameters, then you can define double settle model, and then directly you can just load over here, and then you can directly call to the program during each simulation. For meshing also define mesh there, like one most of the triangular mesh. It's commonly used, and it's quite simple also. But if your solutions are not converging at a faster rate, then you may go with some other meshing option as well. Maybe some hexahedral mesh and quadrilateral mesh. So these things we can just check around. Like this you can just check by just running the simulation early. And if you use the lower number of like coarser grain masses, then your solution may not converge at a faster rate. But your sorry your solution will converge faster rate, but the thing is that it won't be an accurate solution. So for that, we need to go with very fineness, but not up to a maximum extent. Because if you go too much fine, then it will take lots of computational time. Just similar to rhythm mixing, like if you're in FDM, if you're going with very low layer thickness, although you can get very good surface finish, even can get very you can realize very much overlaying quite easily, but it takes lots of time. Similar way in meshing also, it's always proposed to have a some um optimum fellow. So how can you check it? Like basically you can mesh, you can generate the meshes from some certain height, maybe 5 mm, 5 mm, something like that. Then you can run the solution. Then you can get the error. Then again you will reduce it to 4 mm, then 3 mm, like that. You can keep on reducing, and you can find it out. Like after certain size mesh sizes, the solution is not that much varying. The error is quite low. So that from there you can find out the optimal mesh size for the particular application. So once the simulation is done, the next thing is like we need to extract the data, or basically we need to extract the temperature and resource test profile. For extracting, you can directly go to this tab over here, element type. If you go there and select this one, so suppose you want to observe the heat transfer and all, then you can directly go to standard and click the heat transfer mode. So basically you can see over here also like DC38D, DC3D8. So this is corresponding to heat transfer one. Similarly, if you want to go for some, you want to measure some stress, then you can go to C3D8R. So this kind of like this, you can select the nodes as per your requirement, whatever analysis you want to study. And this is one simple example that we have done. Like we just figure it out. Start focusing on reporting on a 100 mm square one. So you can see how the heat is growing. Like we are measuring at the central node, at the center, and at the edge, and you can see the temperature at the center is quite increasing. But if we increase the torch part basically by 750 mm, then you can see at the center the heat is again increasing in a oscillating manner, and the sorry edge, because it's moving from the edge only, and the center part is increasing gradually. And similarly, if you deposit in a 424 mm square, then you can see both are going quite similar. This is an example only to find out the effect of the substrate on the bead. Predict some other other properties as well, like how much residual stress or how much warp or something, not warp mostly the mechanical properties. You can just stresses and all, you can just measure using this process. Then yeah, so this is all about from yeah. If you have anything from the beginning, then feel free to ask. All right, thank you. Hello, am I audible? Uh, Hello.
Yes, sir.
Okay, okay. So, if there any doubt, you can just raise your hand or you can put the chat also. So this toolpath planning and this slicing is quite novel area, and like people are not working that much into this area because mostly people are focusing on material aspects only. But I would suggest like it's a good time to explore these areas as well, like CPP for WAM and all. Not only WAM, even go for the other DED process also. And yeah, so the standard packages won't allow us to try our own toolpaths. So that's why this kind of framework helps you to try your own strategy, your own toolpaths. So yeah, I think it's a good time to start on this direction as well. So any doubt, anything?
Participants may write their queries in the chat.
Uh, Thank you, Brisbane sir. I hope it was useful to you.
So there does not seem to be any queries.
Okay, okay, all right.
So on
Then I'll
behalf of
just
everyone
briefly.
present here, sorry, sir.
Nothing, it's fine. Please go ahead.
So on behalf of everyone present here, sir, there
Yes.
is software problem.
Oh yeah. Or actually, this was developed by our lab, and uh, a toolpath and coding is like it's like a combined effect of all the lab members, and the analysis also like that only. Two members are there which are good in exceptionally good in metal characterization, so they just identified. So it's just like combined effort of all the lab members only. Uh, for software for simulations are like the Abacus is the best one. Like not I won't say best. Like it's like easily you can find the resources in YouTube as well. So it's a good for starting. But if you want to go some fluid analysis also multi-physics problem, then COMSOL and ANSYS is the better solution actually. And but these days, actually, another software like this Flow 3D AM and the AM Prabha, these are some softwares where you can actually predict the melt pool dynamics also. So these are also good, but the thing is that for the computationally, those softwares are a little bit expensive. But in simulation, it's like just like C programming, like you can write anything. So you have much more flexibility in Abacus. So that's why I would like it depends upon you, like what kind of problem you want to try. Like suppose you want to go only for normal stress analysis and all, then I think NCs or will be enough for you. Like if it's all because this already exists in most of the institutes. Seam welding is quite good. Like but thing is that if it is there with you, then you can try. But in simultaneous welding, as per my knowledge, I tried now they have this worm plugin, but earlier I think it was nothing, some toolpath kind of thing, like the one I saw that TSP toolpath, that continuous toolpath. So that is not possible to simulate in simulpact welding or this one, but this is possible in other softwares like maybe Flow 3D and all. So yeah, so in that case actually and another thing is like simulpact is quite focused on this welding and mostly laser welding and like that only. So therefore, if you want to try something else, it, like you have some restriction, like writing your own code, own input, that will be very difficult. Okay, thank you, sir.
Any more queries from the audience side? So if there are no queries, we may proceed to conclude the session.
Okay, sir.
So on behalf of everyone present here, I would like to express our heartfelt gratitude to Dr. Ritam Sharma for his exceptionally insightful and inspiring session. Thank you, sir, once again for your presence and for enlightening us with your wisdom. We look forward for more opportunities to learn and collaborate with you and your institution in the future. Thank you, sir.
Thank you so much. We're also open for collaboration also. And if you have any query, anything like that, and you want to work anything, you can just write to mail to us or sir, or maybe you can directly go to our website also in the amlab.in. So there also we can get many information about the lab and research. So thank you
Thank you
so
so much.
much, sir. Thank you.
So message to all the participants, all the sessions for today are over. From tomorrow, we'll join at 9 a.m. Thank you.